Okay, hi guys. So we'll be continuing our discussion on the equilibrium concepts. So let's get started. So when a reaction takes place in presence of catalysts, rate of reaction is in forward direction as well as rate of reaction in backward direction increases up to a certain extent. Some notes here that when reaction takes place in presence of catalysts, then rate of reaction in forward direction and in backward direction increases up to certain extent. Okay, second point is with the help of catalyst we can achieve equilibrium in same time. Or rather in small time. With the help of catalysts we can achieve equilibrium in a small amount of time, not same time, small amount of time compared to the original time it would have been taken without the help of catalysts. So addition of catalysts does not change equilibrium composition of mixture. Addition of catalysts does not change equilibrium composition of mixture. Okay, and if reaction takes place at non-standard state, then at equilibrium, so if reaction takes place at non-standard state, then at equilibrium we can say that delta Rg at standard temperature pressure or at that temperature pressure would be 0, where delta Rg is the change in Gibbs energy, change in Gibbs free energy or free action. Okay, we'll be discussing about on the Gibbs free energy in our future lectures. Okay, fifth point is that if reaction takes place at standard state, then at equilibrium what will happen? If reaction takes place at standard state, then at equilibrium what will happen is delta Rg at temperature pressure would be equal to 0. Again, delta G naught would be standard Gibbs energy. Okay, now let us see the laws of chemical equation or law of mass action. Law of chemical equation or law of mass action. Okay, so this was given by Goldberg and Weich. okay, wherein we have A moles of A gaseous plus B moles of B gaseous forming C moles of C gaseous and D moles of D gaseous. Okay, then the rate of reaction in forward direction can be written as rate of reaction in forward direction can be written as rate of forward direction is actually proportional to some constant K of forward direction into concentration of A raised to the power of stoichiometric coefficient of A multiplied with concentration of B raised to the stoichiometric coefficient of B, and rate of backward direction is actually proportional to, so let's say I'm not introducing any KF or KB now, so it would be proportional to rate of concentration of C raised to the power of stoichiometric coefficient of C. Similarly, we are applying the same thing to D itself. So at equilibrium, what will happen is that rate of forward direction, rate of reaction of forward direction would be equal to rate of reaction in backward direction. Okay, so in sense RF would be equals to RB, or now I am putting, when I am removing this directly proportional sign, I can write this as RF as KF, which is constant of forward direction, multiplied with A of raised to the power A and concentration of B raised to the power B. Similarly, for RB I can write the same thing. So KF is nothing but into B raised to the power B equals KB C raised to the power C and D raised to the power D. Now we can write that KF upon KB would be equals to concentration of products raised to their respective stoichiometric coefficient and concentration of reactants again raised to their specific respective coefficient. Okay, and this KF upon KB then can now be written as KC. Okay, and KC is nothing but KF upon KB, which is the rate. We are just replacing KF upon KB with a separate constant, so I'm not writing it again. Okay, so this is the equilibrium constant, this Kc is the equilibrium constant. Okay, and if we draw the graph of the same, we can write, or we can draw the graph as, this is the rate of reaction and this is time. So with time, rate of forward reaction slows down and rate of backward reaction also gains momentum, and at this point of time the equilibrium states gets established and then on equilibrium is established. So this is nothing but rate of forward reaction and this is nothing but rate of backward reaction. Okay, so with this we come to the end of this lecture. In the next lecture we will be seeing more theory on equilibrium. Okay, so till then, good luck and goodbye.